Welcome to Maths with EJD. In this video, we'll begin to consider differential equations, which is a very important part of mathematics. In fact, you can consider it as some kind of advanced calculus. All right. Now, let's look at what differential equations are. So we'll start with the definition. Okay. Differential equations. So a differential equation, afterwards, I can just call it DE. A differential equation, DE for short, is an equation, is an equation. Of course, an equation is that which has, you have an expression equal to something. That's an equation. So a differential equation is an equation that involves derivatives. That's where the differential part comes in. It involves derivatives of an unknown function. Derivatives of an unknown function. So when you solve a differential equation, you're looking for the unknown function for sure. So a differential equation describes how a quantity, changes with respect to another. Okay. So we can say that differential equations are widely used. They are widely used in physics. So you have a lot of differential equations in physics, like the Maxwell equations and the rest of them. You have it in engineering, of course, closely connected to physics too, and even other fields like fluid mechanics and the rest of them. In biology, right? In biology, so the growth of body parts, tumors, and things like that. And even in economics, they're talking about the change of one component with the other, maybe how price of things change over time and the rest of them. So let's have a very simple example. Okay, a very simple example of differential equation would be the exponential growth model, the exponential growth model. That is dy dx, dy dx is equal to ky. So this is the exponential growth model. I think it follows the Malthusian kind of population growth exponentially. Now, having talked about the definition, let's look at representation. How do we represent differential equations? Representation. So differential equations can be represented, explicitly, or implicitly. Now, if you remember when I was talking about basic calculus, I talked about explicit functions and implicit functions. So the same idea follows here, because an explicit function is that where you have the dependent variable totally free of the independent variable. But an implicit function is where you have both the dependent and independent variable fused together in such a way that you cannot separate one from the other. So the same thing applies here in a way, except that the representation is just unique here. So the explicit form. So for the explicit form, right? Um, for the explicit form, the highest derivative, the highest derivative is isolated. The highest derivative is isolated. For instance, imagine that you have, okay, the example here is that you have d squared y dx squared. D squared y dx squared is the highest derivative, and that is equal to x plus y. So you don't have the highest derivative mixed up with anything on the other side. Okay. And we can also talk about the implicit form. Implicit form. So for the implicit form, right, we have that the the highest derivative is not isolated, is not isolated, okay, from the rest. So a very good example of that is the is x d squared y dx squared plus y equals 0. So this is implicit because the highest derivative d squared y dx squared has x squared joined to it. Whereas in the previous case, it was standing on its own. So you have implicit and explicit representation like that. Now, can we also talk about the formation? So let's talk about the formation of differential equations. How are differential equations formed? Okay, differential equations can be formed in different ways. It can be formed through the process of modeling, which you are going to see a lot of. Maybe you talk about a population growing and things like that, just like what we have seen before. But another very good way of forming a differential equation is through what is called primitives, right? Let's say so is formed. A differential equation is formed by eliminating by eliminating arbitrary constants. So you eliminate arbitrary constants from a given function, from a given function. So the function, it is the function you can call primitives. So a very good example will be this. Example. So given y equals c1 e raised power x plus c2 e raised power minus x. So if you have this, right, you can differentiate the first time, you have dy dx equals if you differentiate this whole thing, you have c1 e raised power x, and then if you look at this part now, e raised power minus x, so the minus there comes down, so we have minus c2 e raised power minus x. That's first differentiation. The second one, you have d squared y. You have, if you differentiate the second time, right, you have d squared y the x squared, and that means you have c1 e raised power x again, because e raised power x remains the same all the way. The minus comes again, so you have this plus c2 e raised power minus x again. So you see that now we have gone back to where we came from, because this part now, let me color code. So you see this part now is equal to this part. So it means that we can say that that the squared y now, the x squared, is equal to y, the y we started with. So the squared y, the x squared is equal to y. So that means we can form a differential equation, which is the squared y, the x squared minus y equals 0. So you see, this differential equation now, the solution will automatically be this because of how we proceeded. So at this point, we have eliminated all the constants, and that is how that goes. So a very good example again, that example, if you can take that as example one, okay. Let me call that example one right there, example one. So I want to give another example like that involves polynomials. So look at example two now. Example 2, imagine that y is equal to ax plus b. Let's do this very simple one. So the two constants here are a and b. So we can form a differential equation from this. The number of constants you have will determine the number of times you have to differentiate to eliminate all the constants. So you have a and b as constants, so you differentiate twice. So the first one, you have dy dx. Of course, yeah. I mean, dy dx is also y prime, by the way. Okay, so you can, if you differentiate the y with respect to x, you get y prime. So I want to also show that to show that I don't have to write dy dx. So it can be y prime, or sometimes it's y dot, which is, I mean, sometimes, okay, maybe I'm going to talk about that later. Or let me even say it now. So if you have dy dx, most times we represent that as x prime. I mean, we represent that as y prime, okay? That will be y prime. But then if it is with respect to time, maybe dy dt or the x dt. So if it is the y dt, that's y dot. So when you see dot, you know you are differentiating. So y is a function of time, but if it is prime, it's a function of space. So x is space. So you can pay attention to that in case we come across that later. So here y prime, especially when you talk about dynamics and all the rest, which where time is involved, we have y prime equals differentiate. So you have a, because b is gone, because b is constant, so we don't have that anymore. So that y prime prime okay. Okay, one thing we can now do is now y prime is a, right? Since y prime is a, like this, so what we're going to do next is to say, okay, let me go back. Y prime. Okay, I don't think I have to do all this. Yeah, this is y prime, right? Y prime is equal to a, We know that. So since we have got y prime to be a, so we know that it means that y is equal to a, that is uh x y prime plus b. Should I even do this? Trying to see. Y prime is a, so b is automatically gone. So because so we can actually have, we can substitute that a into where we are coming from. So if you put y prime for a in the first equation, okay, so we can say we have y equals, or let me put the color back. So we have y equals x y prime plus b. But we see b is still here present. Um, so if we differentiate the second time, if we differentiate the second time, we have y prime equals, now this can be in two ways now. So we have x, we can, if we keep y prime constant, we have x, we can have x y prime prime plus um okay, trying to see what exactly this should be like. Y prime is equal to a, right? Plus b. So dy dx. Okay, here now, so we can have x y prime prime, and then we now have, when we differentiate with respect to x, we have just y prime, and b is gone. So at the end of the day, this is what we have. Okay, this is not making any sense. I guess I need to rest this. I guess I need to rest this, or better still, okay, let me come back to it later. Um, right. So from all we can see from here, right, we see again that y prime minus y prime is equal to xy prime prime. So at the end of the day, this just cancels out. So we have xy prime prime is equal to 0. That is x d squared y dx squared is equal to 0. That's the differential equation from it, having eliminated both a and b. So we basically form differential equations from functions by eliminating the constants we have in the functions. So with that done, we are good to go to the next thing. So we've seen formation of differential equations. So the next thing we'd like to talk about would be types of differential equations. Types of differential equations. Okay. Um, so the first type of differential equation will be the ordinary differential equations. Ordinary differential equations. So which we'll be calling ODEs as we move on. ODEs, ordinary differential equations. ODEs, ordinary differential equations. Okay. So in this case, right, um, ODEs depend, ODEs depend on a single, independent variable, on a single independent variable. Okay. So, and a very good example of that is this. Okay, let me go this way. They depend on a single independent variable. So you have d squared y dx squared plus 3 dy dx plus 2y equals 0. So as you can see, right, we can say that this is coming from the fact that y is a function of only x. And that is why we have d squared y dx squared 3 dy dx and all that. So y is a function of x. That's what that simply tells us. But then we have the opposite of this, which would be the partial differential equations. So we have differential equations, partial differential equations. Interestingly, under the playlist on numerical analysis, I talked about how to solve ODs and PDs under the ideas of initial value problems and boundary value problems. Okay, so for partial differential equations, right? They involve partial derivatives with multiple independent variables, with multiple independent variables. Okay, those are partial differential equations with multiple independent variables. So a very good example of this example, okay, um, so a good example of this is what we know as the Laplace's equation, the Laplace equation. So the Laplace equation is partial squared u. So you see partial is what we use here, partial squared u, partial x squared plus partial squared u, partial y squared equals 0. So what it simply tells us is that here now we have u to be a function of both x and y. So u depend on x and y, whereas up here we have y depending on f and x. Okay, so u equals, so once we have more than one dependent variable, then any derivative you're going to get from that is going to be a partial derivative. So because you're now going to differentiate with respect to those. So that we see generally speaking for if I have to make a table and we have ordinary differential equations, we have ordinary differential equations, we have partial differential equations. So and we want to compare them. So the first thing is that okay, we have, of course, they both have one dependent variable. Okay, so um, one dependent variable, one dependent variable, and one independent variable. Clearly, one independent variable. And here we have one dependent variable, one dependent variable, and two or more independent variable. So that's talking about variable types, right? Um, maybe I should say here, maybe I should actually talk about variables here. So we are comparing variables. So that's the first thing. One dependent variable and one independent variable. That's one. Then two, let's talk about representation. Representation. So for this, we use full derivative. That's complete derivative. That's dy dx, or we can have dt, I mean dx dt, dx dt or dy dt or anything. But here we have partial. So maybe we have partial f, partial x, partial f, partial y, okay? Because we have more than one variable, right? In fact, I think to drive the point home, it's better um I just leave it as dy dx, right? Okay. So in essence, what we are saying here is that this implies that y is a function of x. But here we say that f is a function of both x and y. So this implies that f is a function of both x and y because we have more than one independent variable. Okay. So So, well, I just want to stretch it and talk about derivatives, which we have said already. So for the derivatives, right, here we have complete derivatives. We have complete derivatives here. And here we have partial derivatives because you are differentiating with respect to more than one variable. So that's a very simple comparison we can make. And of course, they have their various kinds of There are other things we can talk about, like when we get to talk about some classifications along the line of whether they are initial value problems or boundary value problems. So come along. We're still going to talk about all of that as we go. So that's talking about types of differential equations, basically ordinary differential equations and partial differential equations. Ordinary differential equations, you have the dependent variable with one independent variable, and for ordinary differential equations, right? One dependent variable and one independent variable. For partial differential equations, you have one dependent variable and more than one independent variable. Okay, so now let's switch gear and talk about let's switch gear now and talk about, say, what we call the some terminology and basic classification. Okay. Um, right. So, mm, I'm thinking I should stop here. Okay, let me stop here and make the next one into another video. So of course, be sure to subscribe to the channel and hit the notification bell so you can always get alerted each time a new video is released. So in the next video, I'll be talking about terminology and basic classification because this one looks long already. So let's do that. Of course, let me know how helpful these videos are for you. Let me also know if you need me to teach a topic or solve a problem. Till I come your way again, keep doing maths right. Bye.